Cool. So going to talk a bit about generative modeling and some cool recent applications of it. As a quick overview, generative modeling, and particularly the areas that I'm interested in, is modeling complex high-dimensional data. So a bit of the opposite of a lot of lower-dimensional data like time series. And recently, deep generative models have been making a lot of progress here. There are various reasons why we're interested in this kind of stuff. Unsupervised representation, manifold learning. Understanding better some of the discriminative models we use, because we can oftentimes cast them into their generative counterparts and understand them better through that. Some more traditional things like density or likelihood estimation. This could be used for outlier detection or various other things. Conditional generative capabilities. A good example of that would be like text to speech. So being able to synthesize audio conditioned on the text that we're trying to generate from. Additionally, sampling can be useful in various end applications, particularly in more creative aspects or something like that. So yeah, here's some quick overviews of some recent work on generative modeling. So on the left, we have a chatbot. This is a recent one from Google, and it's a chatbot. Takes in a comment and tries to learn a conditional model of the likelihood of a response. So this is a fun little discussion on morality. My favorite part is the second question, where the person asks, "What is immoral?" and it responds, "The fact that you have a child." Anyways, these things might learn some weird things. It's just a generative model, and it has probably given the likelihoods these models have, it probably had 20 choices to choose for when it picked child. So there's 20 other things it probably could have said there, but it picked child that time. In the middle, we have an example of generative modeling of images. So this is a recent work by DeepMind, and this is something called a pixel RNN. And what we're trying to do is, what this is showing is samples from this model, and it's basically taking a data set called ImageNet 1K. It's about a little over 1 million images. About 10% of those are dogs, so that might explain some of the vague dog blobby shapes. And you can see they're kind of these really visceral, like, bright colors, and if you keep looking in, it's kind of hard, I imagine, for people farther back. You don't really see too much structure, but you can see some global structure and some trippy, like, kind of very intertwined, mixed up colors down in the details. But it kind of gives you a sense of where this space is today, because it's very high dimensional data. We're talking about a like 20,000 dimensional problem here. And we know there's tons of structure inherent in these kinds of problems. And therefore, it's pretty difficult to get an arbitrary sample to actually be a realistic looking photo. And on the right, we have an example of handwriting generation written by a handwriting generation model. Yay. Thanks to Alex Graves for providing that demo on his website. And so all of these models here actually use a single class of algorithms called RNNs, recurrent networks. There is also another class of algorithms called CNNs, and I think there was a previous presentation that covered those in a decent amount of detail. And basically, these are two, when you hear a lot about, deep learning and yay, cool stuff, or now we're just saying, deep learning equals AI or something like that. I don't really know what's up. Usually, we're talking about applications of these two sets of algorithms. Convolutional networks, which are great for image processing and are recently finding other applications in areas like text and speech, and recurrent nets, which are kind of this pretty general class of algorithms on the right that basically take in inputs. They are self-connected so that they can talk or keep context or pass state information over time, and they can spit outputs out when you want them to. So underneath the RNN visualization on the right, what we have actually is showing, for instance, what one of these things can learn. And this is looking at the activations of one of the cells in this model as they track it, and it's basically a heat map. And you can see that, for instance, this one keeps track of whether you're in a URL. So you can see it lights up green when we're inside of a URL. And you can imagine if you have a generative model of language, this model is trying to say, given the previous character, predict the next character, and you just do that, and eventually you get a sequence of English gibberish. You can see how like this kind of state information of like, am I in a URL or not, is really interesting and really useful features for like a generative model to learn. So those are the two classes there. Once again, I'm going to keep track of time during this so I don't go too long. So those are the two classes. A CNN, again, I think I imagine one of the previous presenters talked about that. But basically, we have a series of hierarchical filters with nonlinearities. And you can see on the bottom left, some nice, cool first layer filters that thing learns. And those are applied all across your image. And it's basically dealing with structure and spatial information. Whereas a recurrent net just has a time dependency or a sequence dependency, effectively, which is great for something like text, where it's a sequence of characters, words, bytes, etc. So These are all nice, pretty pictures and yay handwriting and yay images and yay chatbots. But, is this stuff actually useful? In general, we talk a lot about, discriminative modeling. So here's one example of a useful generative model. This is something called Skipthought vectors. And the core concept here is we want to learn a representation of a sentence. And that is the goal we're trying to set out to accomplish. So it's not really clear how we could go about that. But one idea is, well, we can learn about things by the context in which they occur. So we're going to take a sentence and we're going to try and train a model to be able to generate the previous sentence and the sentence after it. So you can see that it could read in, I could see the cat on the steps. And then it splits off into these two other models that try to generate the sentence before, I got back home, which would be reasonable. And then the sentence after, which is, this was strange in this case. So that's literally all this model is. It's a generative model. It's taking in a sentence. So it's a conditional generative model. It takes in a sentence and it tries to generate the previous one and the next one. And it turns out that the representations this model learns to generate these sentences can actually be quite useful. So we show on the bottom, for instance, 3 different data sets. TREC, which is a series of questions, basically classifying what kind of question like you can imagine these as like Jeopardy questions. Who was the 13th president of the United States, or this person was born, and like the goal is to say, is this asking about a person, a place, time, or something like that. And you can see that this model, without ever being trained on these data sets, so we actually trained this guy up on about 10,000 books. To clarify, that sounded like we. That was the royal we there, my bad. This was actually work done by the University of Toronto, primarily a guy called Ryan Kuros, really awesome. We're developing these models internally as well, but these are results from the paper that's publicly available. So this is trained up on about 10,000 books. It's about 1 billion words. It takes 2 weeks. It's a big RNN. You have a lot of GPUs, et cetera, et cetera. And we can see on these data sets, this is a clustering visualization colored by the relevant semantic property we're trying to pull out, that without ever seeing any of these data sets, it naturally clusters in groups, in some cases quite well and basically linearly separably, some of these semantic aspects of text. So the first one is like asking about what kind of entity is this piece of text we're inquiring about. The second one is subj, which is a subjective or subjective data set. So it takes movie reviews and it's trying to classify whether a sentence is basically an objective one, saying like, Tom Cruise has not been in movies since 1999 or something, versus like, I did not like, the way that he acted or something. So that's a subjective, and the prior one being an objective. And finally, the last one is sick, which is a weird name for a data set. And primarily it's trying to measure sentence similarity. So what we do in this case is we actually embed vectors coding the differences between the sentences we're trying to compare. And it's kind of surprising that you can see, even just using these raw representations, that the space that our projection of the space here that we see, the more similar sentences and the least similar sentences are actually kind of grouped together. And that might make sense given that it's trying to, predict the sentence before and after. And so it's kind of internally doing modeling of similarity and things like that. So this is one example of where generative models now can be used for useful properties. And briefly, now we're going to transition a bit more into some of the details instead of these high-level overviews. So there's 2, I'd say, promising areas of approaches that have recently been developed in this space, where formerly we have some input distribution or data X. And how do we generate data drawn from this distribution? This is primarily from a sampling-driven perspective. So there's 2, I'd say, camps right now that have a lot of interest in them. Variational autoencoders are more generally probabilistic graphical models with approximate inference. And basically what these look like is you have an input example. It goes into an encoder block, which is an arbitrary function. It outputs to some representation space, Z. This, you could draw this encoder diagram. It could be PCA, it could be, a deep network in this case. It doesn't really matter. This is just a high-level architecture overview sketch. And then you have a decoder, which takes that representation space and attempts to project it back to the input space. So that's pretty standard. The details, we'll go into in a minute, the details of what makes a variational autoencoder, but that's a pretty standard diagram if you're used to seeing a generative modeling, some modeling aspects of unsupervised data, for instance. There's one other class of really interesting algorithms that have been developed recently, also called generative adversarial networks. And this is a really cool kind of way of turning the problem on its head, where you see, as before, that we have this Z space that a decoder takes and projects back to the input or data space. And so a generative adversarial network has that as like it's the way it works, is it takes in some Z space and attempts to produce samples from the distribution. And the way we actually do this is by having what we call a discriminator, which is another model that looks at the potential samples generated by this generator process, and as well as real data. And we actually use gradient descent to learn the generator as we train this discriminator to effectively do like a contrastive estimation of what's real or not. You can think of it as this discriminator sees, initially random noise from the generator because it's just like randomly initialized. And it also sees real data. And as it learns how to discriminate the noise from the data, it has to capture some information about the actual data. And therefore, if we try to make the generator fool the discriminator, and we'll get into the algorithm details in a bit, it can actually kind of, as we'll see, learn to capture the data. And it does it in this really interesting way. And it's kind of this, you could almost think of this as like a Plato's cave analogy if we want to go all freshman philosophy on it. It never sees the actual data. It only sees another model's view and representations of the data. So back to the variational autoencoders real quickly. So they're theoretically elegant autoencoder. Again, we call it an autoencoder because it has an encoder and a decoder, and it's attempting to encode itself or data or whatever. So that's apparently where that name came from. And basically, the key concept of variational autoencoder is the way we define the Z space or representation space is we have a prior space, like let's just say, standard Gaussian or whatever, independent units. And we impose this prior on the code space. And this allows us to regularize the model in one way because it's not just an arbitrarily unconstrained representation space. And it also allows us to sample from this model because if we've forced this encoder process to be approximately mapped onto a simple like representation space, like an independent Gaussian, then ideally, if it's done that process well, we can just randomly generate, Gaussian noise according to the prior distribution, and then decode that back to the samples, back to the input space via the decoder, so we can get samples. And there's some math involved, and it turns out it's doing something that's theoretically legitimate. But I tend to view things in a more kind of engineering practical perspective. So we're just taking an arbitrary code space, imposing a prior on it, regularizing towards that, and that kind of constrains things and allows us to sample from it. So on the right, you can see, for instance, if we just have a two-dimensional code space, and we just go over the distribution there on like a faces data set, and oh god, it's MNIST yet again. You can see that it kind of has a cool way of transitioning, and it kind of learns how to compactly put things together in this very small space to transition and rotate and twist and expand and shrink. So yeah, that's variational autoencoders. And I talked about the prior on the code space. These things are trained to minimize reconstruction error as well, like a standard autoencoder. So they're taking an input example, and via this encoder and decoder process, they attempt to recreate that example. So that's a maximum likelihood style method. And usually we use just like mean squared error independently on all the pixels, for instance. It's a very, very loose reconstruction function, but it's correct. And we'll talk a bit more about those distinctions there. But you can see how like a reconstruction style function kind of encourages blurringness and collapsing of the data space, as you see in like this very limited representations with the MNIST manifold. So let's go a little bit back into that generative adversarial network thing instead. So again, we have a Z space, and like in an adversarial autoencoder where we say, oh, it's just going to be unit Gaussian, we can just say, yeah, you're going to deal with random noise, and you're going to have to learn some functional mapping from that random noise to the actual data distribution we care about. So the training loop for this diagram basically looks like sample random noise, also sample a set of random examples from your data set. And then what we do is we update the discriminator with this contrastive estimation style technique. Basically, you can think of it as just a binary like logistic regression model. You could literally train this with logistic regression. It probably won't do much interesting, but for simple problems, it might work out quite well. So you just try to train it as a standard classification problem, differentiate real data from samples from the generator. So we do a step of gradient descent for that. Then we sample another set of noise samples, and we update the generator by descending the discriminator's gradient. So we try to fool the discriminator And we use that fooling signal via gradient descent to have the generator learn how to generate real data. So we try to make it think the generator's data is real and don't worry about messing with what real data actually thinks in the discriminator. So this is a two-player game, and you can think of it as you do basically you're doing a bunch of sub-step minimization between the two. It gets kind of weird. No one really knows quite. If it's convex, it converges. If it's not, no one knows what's going on, and we're trying to figure that out better. You can use any standard gradient-based learning rule. Again, we have the requirement that the generator and the discriminator are differentiable in this case. And yeah. So here's a little GIF. Does the GIF work on the TV? Yes, it does. Yay. So you can see, for instance, here's just it's trying to model a standard, simple, unimodal Gaussian in 1D, and this is the learning process of this game. So I'll wait for it to reset real quickly. You can see that as it starts, we've got this P of data, which is the actual underlying Gaussian we're trying to learn to generate from. D of X is this discriminator function that is looking at the probability it thinks it's real data, is that red line. And G of X is the actual generated distribution averaged over a bunch of samples from the generator. And if you watch it, you can kind of see how it's this, like, the gradient would be the derivative of the line D of X. And you can see how these kind of like little wiggles happen back and forth. And, you can see like right now that there's this kind of sharp one on the right side of the D of X, and eventually the generator is kind of smoothing that out over time. It's basically just following and learning to spread and move the probability mass around based on this D of X function. So if we look in the bottom right here, we see some samples from these various models. And one thing, it's not apples to apples, but like if we look at those MNIST samples in the upper left, one thing that's kind of interesting and clear about this is it's a very different mode of the visuals of these models than like the MNIST manifold from the VAE. And that's because, again, we don't have like a simple reconstruction term here. It's using effectively the space in which it's optimizing for the data is a learned space by the model that is trained by the discriminator. So we're basically optimizing for similarity in a learned representation space instead of using a raw like maximum likelihood space of like, independent pixel style reconstructions. And this is really useful, again, potentially for high dimensional data where, a prior function to optimize like independent mean squared error of pixels is not really all that good at guiding your model. Because, for instance, images have so much structure, but a cost function or objective function like that doesn't really capture that. There are various extensions of VAE that that kind of incredibly, increase the sample quality, for instance. So if we look on the left, semi-supervised learning. So this is really cool. You can jointly optimize an unsupervised and a supervised objective together. And ideally, you can learn how to use information from the unsupervised task of recreating the digits and the supervised task of like classifying which one's which to kind of factorize out your representation space, where you can have these analogy examples effectively. Where if we look here, we see that you have like you have this leftmost digit, which is like the example that we want to reason about. And what we do is we pull out the representations that we know are related to the aspect or appearance and not related to the classification problem, because we factorize our representation space. Instead of just having this Z here, we also have a C for like the classification space to represent the semantic thing we care about. And then we can change the C values with that given Z. And we can see that like for the first one with that bold fat 4, it has, a bunch of bold fat 0, 1s, 2s. So that's kind of cool. We've disentangled the thing from the what from the how, or the how from the what, or whatever. You get the idea. On the right, we have draw, which is an extension of VAE, or again, a probabilistic graphical model optimized via approximate inference, to be a RNN, specifically an LSTM, that writes to a canvas over time. So this is actually an algorithm that draws. And you can see the example on the MNIST example, over time as we move from left to right, you can see how it kind of learns to draw 3s and 8s and 7s. And unfortunately, it always draws from bottom up instead of from top down. So it's not how we do it, but maybe we should do it that way. I don't know. And then on the right, you have samples from a data set called CFR10, which is just dogs, cats, horses. Super tiny, again. Everything's so tiny so far, but these things can be slow. 32 by 32 pixels. And you can see it's much sharper than like the you know, the blurry MNIST samples from before, but it's still this kind of blurry stuff. And so kind of a potential reasoning why we're still investigating why these kinds of, you know, these approximate probabilistic models often tend to generate these kind of blurry, fuzzy things. It might be because we're using this kind of naive, straightforward reconstruction term with like independent maximal likelihood style estimators. And those, you know, implicitly, if your model is underfitting, and because images are very complicated high-dimensional data, this is a pretty reasonable assumption, given that we are only just scaling up supervised image classification algorithms, and they're way bigger than basically any models we've had before. In that underfitting regime, you kind of hedge your bets by blurring and smoothing everything out. And you know, if we're caring about samples and end user applications of potential uses of generative models, this can be undesirable behavior. Equivalently, you can think of underfitting for like a chatbot as producing like very general, vague sentences. Like a pretty decent chatbot that super underfits to your data is just going to say thank you or great or yes to every single question you ask it. And you can think of these kind of blurry, fuzzy input images as like being maybe a little too close to the thank yous or yeses, and less close to the fact that you have a child kind of things. Cool. So there's extensions of GAN. So this is one with one of my collaborators on the project we'll be talking about in a minute, called LAPGAN. And basically we take that generative adversarial problem and we phrase it as a hierarchy where we start with a low dimensional small image, and we try to learn an upscaling algorithm that takes a small like 4x4 pixel algorithm and tries to produce an 8x8. And we just do that, you know, go to 8x8, then go to 16x16. We have a chain of these. And you can see samples from this on the right. And they are, again, they look like what we expect from a GAN. They're sharper, they're clearer, and these are supposed to be churches on the top. You know, you can kind of see it, the towers more formally. You can see how there's like kind of a peaky gray blob mass kind of thing. And cool, because this process is stochastic, because we have this GAN sampling from a prior distribution, if we start with these very low dimensional fuzzy images on the left, you can see that every time we run this generative process, it actually produces a slightly different high res image. So now's the point where I stop talking about what I did, because that's usually how these presentations go. So this is a collaboration between myself, my coworker, and Sumit from FAIR. And this is an extension of GANs that we've developed called deep convolutional GANs, or DCGAN. And we believe this is currently one of the best, at least in terms of sample quality, models we can do of generative images. So what this looks like is a big CovNet. We have that prior space Z all the way on the left. And what we do is we invert a standard CovNet. So a CovNet is generally a discriminative algorithm. You know, we take in an input image and we try to map it to some, you know, classification or regression problem. This is the other way around. We're taking some latent space. It's like the decoder, and we're just going to do deconvolutions or convolutions that you just transpose the weights. And where you have a stack of these, in this case, 4 layers of them, and we go from this 100-dimensional space, we project it linearly to a effectively, in this case, approximately 16,384-dimensional space. And then this is like a high-dimensional like image representation, a 4x4 grid by a lot of information dimensions. So this is typically the kind of representation you see at the end of a large supervised convolutional network. And via a series of steps, we upsample that spatial resolution from the small scale wider and wider, because we know eventually an image is like 64 or 128 by 128 pixels, so we got to get there somehow. And we shrink the information size because, well, if we could, we'd probably keep them big and fat all the way through, but computationally we can't do that right now. We also use strided convolutions here. So instead of applying the convolution kernel at every single pixel subspace, we apply it with stride 2. And this is actually how we do the upsampling. And it's the gradient pass of a strided convolution forward pass, and that's the fundamental operator we use here. No fully connected layers. We use a bunch of tricks. If you're a deep learning kind of person, these should be familiar. If not, they're just tricks of the field. And here's samples from that model. So we can actually get really kind of in that uncanny valley style samples from at this point. If we look at the faces on the left, there's some kind of disturbing stuff going on there. Again, if we think about what it does, it takes that 100-dimensional space and it projects it to a 4x4 grid kind of independently and linearly. One of the issues we've noticed right now is, for instance, some of these faces, if you look at them, they kind of look like they are like half there, and like the other half is like not really correlated or constrained well. We think that's because of that simple linear upsampler, and sometimes that patch over here just doesn't mix with that patch over there, and then you get someone who's like half their face is like, you know, looking this way and the other half's looking that way, and it looks really distorted. But there's a lot of crispness, a lot of sharpness. The discriminator is, again, another covenant. And because of this, we've structured our discriminator, and we've structured this like similarity space to be learned and to be a covenant with all of this prior information encoded about spatial similarity of pixels. It therefore optimizes, instead of in pixel space, in this kind of much more visually, you know, cohesive space of you know, faces, we could say. You know, one interesting thing to note, for instance, is like the hair textures here. If you look, it actually has incredibly fine detail of like the textures of the hair. So this thing is kind of obsessed with hairstyles. But when all you've got and the only thing you know about the world is a million pictures of faces, hair textures are kind of an interesting thing to pick up on, I guess. Anyways, so those are faces. You know, that's not the most impressive per se. It's a very constrained distribution. You know, it's basically a frontal face. We have great variety over them. You know, there's all sorts of changes, and there's hats, and there's bright, and there's dark, and there's, you know, glasses and no glasses, and you know, lots of stuff going on there. But it's still like just a frontal face with not very much changed. On the right, we have bedrooms. The only reason why we use bedrooms is because we have 3 million photos of them. I don't know. That sounds really weird. This is a data set called LSUN. It's by Princeton. Princeton did the dirty work. And they basically have a data set of a bunch of scenes, common scenes. So like kitchens, bedrooms, like living rooms and bridges and those kinds of things. But we just, you know, we want really ridiculously huge data sets to get really ridiculously good samples, and to prevent overfitting. And so on the right, we see those bedrooms, and it's pretty reasonable. You know, it seems to have figured out, you know, the geometric spacing structure of a room. You see bed shape objects, you see windows, you see doors. It's kind of cool that we have a model that can take a bunch of arbitrary photos, again, just of bedrooms, and it kind of seems to have figured out that, oh, there's these window things and these bed things and these door things. And we can show that if we, in general, if you show this to an academic, their immediate response is you're overfitting. And that's a very understandable thing. So we have to do a lot of stuff to show and demonstrate that we're not just like learning to copy input examples. So we can, for instance, show that it can interpolate between these bedrooms in very semantically reasonable ways. You can see how like a picture frame will morph into like a window, or, you know, fade out into like just a wall, or a door will change into, you know, a bright white door, or a window will change into a bright white door, for instance. So it seems to have, you can even see, like, if you look at the tops of the images, how it like shapes the room structures to be between like looking at a corner versus looking face on. Additionally, what's a very interesting property that we found these models can do on constrained distributions is they can actually learn vector arithmetic. So if you're not familiar, there's like this kind of very like, you know, hello world example of like representation learning via like this, you know, class of like, sometimes it's called, you know, a deep learning algorithm. Basically, like, there's this famous example of you take the vector for king and subtract the vector for queen and add the, I always mix it up. So basically, you take king, you subtract man. So now you have like whatever the kingness is separated from the gender, and you add woman, and the result in this vector space will be, the closest vector will be queen. This is kind of a quintessential example, and we can learn these on text in an unsupervised manner. We've shown that these kinds of models appear to be doing similar things on images as well. So we can take a man with glasses, subtract the manness part, add the womanness part, and we get pictures of women with glasses. You know, we can take a person who's smiling, subtract the smile, add a grumpy face, and then we get them smiling. And additionally, we can show like that this actually can do like interpolations between like looking left and looking right. So you can see like the quintessential looking left vector and looking right vectors, and we can just take any arbitrary sample in the middle there, and we can shift its representation into either of those directions, and we can see how it can rotate or translate. And all of this is linear in the representation space. It's just a 100-dimensional uniform space, but through this deep convolutional network, we can, take these linear shifts and make them back into complex nonlinearities in the input space. And so that's really interesting from a representation learning perspective. And we're continuing to explore ways of assessing and seeing the usefulness of the properties of these kinds of models. Additionally, we can show that that generator appears to have separated the representations in the intermediate layers to, for instance, have its windows. So we can actually take that generator, look at the units or subsets of it that activate when they are around what appear to be the windows it generates, and we can just get rid of all those units. And then we can make it do its generative process again, and you can see that it kind of forgets how to make a door or a window when we get rid of those units. So that suggests it's disentangled and is actually learning kind of how to represent windows or doors separately. And it makes sense when you have a small dimensional representation space, you need to be able to be efficient with the computation you have. And so one of the possible things it can learn is to group together generative processes for windows and doors and make use of the efficiencies there. We can also show that it learns object detectors. So if we train it on faces, it actually has units that basically are, this is entirely unsupervised. Basically, this unit fires when it sees glasses. So you can get a glasses detector for free if you have 1 million examples of faces. It's not perfect. The first, I think 18 are all glasses. Sorry, there's that one bizarre thing with text in the third example. Like it's not perfect. This is not going to ever be a supervised thing, but you can get it for free if you just happen to have 1 million faces. And so then these are, again, validation examples. So this also shows that the representations it learns generalize to real data and new data, and it isn't just perfectly overfitting how to copy input examples, for instance. Here's some numbers. It, in general, does quite good. We since need to update the Street View house numbers because, again, this is an entirely unsupervised model. And so currently in the research community, we're figuring out how to best have unsupervised representations match supervised representations. And in general, they tend not to. And so when we benchmark things on supervised tasks, oftentimes it can be kind of unfulfilling. And so it's not immediately clear how we take an architecture like a DCGAN and convert it into a supervised classification task. And so, one of the traditional things in the literature is to just take the filters and to just take the representations of, for instance, the discriminator in this case, and just then fit a supervised model on that small subset of data. We can beat, for instance, a standard supervised CNN on the same amount of data quite significantly, 28 to 22%. But there's been some recent improvements in doing this semi-supervised technique where it's using an unsupervised model in addition to a supervised model in the course of training. And it looks like these techniques are getting much better at extracting out relevant information and doing both tasks at once. So these results have been beaten down to like 16% in the last 2 months. And even more embarrassingly for us, that's by a fully connected architecture. So it's clear that there's some work to do on figuring out how to get these representations potentially useful for supervised tasks. But if you're looking for generative models that make pretty pictures, that part of this seems to be consistent. And there just needs to be further work on figuring out how best to use these representations and figure out, for instance, semi-supervised extensions. Cool. I don't want to keep y'all too long, so I think I'm already 10 minutes over, but yeah, let's finish out real quickly. So this is, for instance, a conditional generative model here. We use a DCGAN, but we tell it which example it's trying to generate. And we can show that our convolutional extension of a normal GAN does significantly better. And unfortunately, it's MNIST. But if you look on the right side, every single one of those looks like a valid 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's basically captured the underlying data distribution of manifold. We can actually, for instance, use this generative model. We generate 10 million samples from it, and we know which class it was from. And then we can do a stupid naive algorithm like nearest neighbors classifiers on that. So we can actually get a nearest neighbors classifier on MNIST to beat a very bad traditional network, or we can actually get it to be an RBF SVM. So we can have naive nearest neighbors if we expand our data set via generative model to 10 million possible samples, beat like a RBF SVM of olden days using naive nearest neighbors. So this is primarily an experiment to test how well we can capture the actual data generating manifold. And if you keep generating samples, eventually we'll fill that manifold. Sure, it's 784 cursive dimensionality, et cetera, but let's see where this goes at 1 billion samples if we're willing to wait forever. Additionally, we have some other results we're working on to have conditional conditional version of DCGAN that take in text and generate images. So this is on a data set of, actually, if you know Reddit, it's this is r/earth porn. It's just entirely photos of, like, beautiful photos of streams and rivers and whatnot. And we just train it on that. So it gets in a piece of text and it tries to generate the actual image that we're seeing. So we're trying to have, models that can, effectively have, okay, whatever. People always go over the top with this, but like imagination or something, and they can, think about something, and you can see all the different things it's thinking about, et cetera, et cetera. So real quickly, what this is each of the text examples is a column. Each of the text examples is a row, and we change that samples through that latent space Z. Again, it's like a semi-supervised VAE where we have that Z and that C. Here, that conditioning vector is the text, and then sample from the prior space. And you can see that, like, for the beautiful falls and streams, for all those samples that basically kind of paste these watery textures and, blue stuff in the middle. And like, for instance, you can see for the second one, it's kind of this, like, oh, there's some sky and there's some earth. And you can see that, like, for the one that's like Sahara Desert and sand dunes, it, like, turns it into, like, sandy looking. And you can kind of see that consistently throughout, like, all the Sahara Desert and sand dunes ones, how it kind of makes it a more deserty scene. This is some really exciting work that we're still exploring. Can be a little shaky. These models can be a little unstable. So we're continuing to explore extensions of them and how to stabilize them and how to keep them working and to more understand what's going on here. Additionally, you can hybridize a VAE and a GAN, so you can get the best of both worlds. You can have the stability of a standard, doing a theoretically correct thing like a VAE, and you can have the kind of learned similarity space of a GAN. So this is some really cool work recently on jointly training VAEs and GANs together, and they can kind of get a middle ground between, like, the very creepy, like, uncanny valleyness of the GAN and the kind of smooth, like, simpleness of a VAE, at least with the current architectures models we use. Cool. All right. Thanks. Questions? Yeah. Yep. Yes, totally. So if we get generative models to eventually be, right now they're in this, like, middle ground. So, like, on MNIST, this example here, I'd effectively argue, is exactly that. It's data augmentation, and we can show that we could use this big complicated model to make a simple model do quite well on augmented data. So that's exactly one of the avenues we've been exploring. And if we could imagine several classes of those kinds of transformations that could be useful, this is potentially an exciting way to learn augmentation of your data from the data itself. Yeah. Yep. Are you exploring adversarial autoencoder? Yeah, totally. So I think that's a totally other exciting avenue, and they're a little more stable and more straightforward. So they're also really interesting. So we've been looking into those guys as well. Adversarial autoencoders, I can give the 5-second thing on them, or try to. Basically, we have a prior distribution for Z, right? And so with a VAE, we have an analytical term for what that distribution should look like. So that's great. If we know a Gaussian, all the math works out, great. We can optimize for it explicitly. But when you want to go to, like, an arbitrary distribution for that, for instance, like, let's say we want our data to be on the Swiss roll. Like, how are we going to derive the formula for the likelihood of the data from the prior of a Swiss roll? You can probably work it out, but you can see how, as we extend that, eventually we're not able to mathematically derive an exact solution for, like, this prior space. And so an adversarial autoencoder is an extension where we have a GAN deciding whether our representation space is actually from the prior or not, because all we need is samples to have a GAN figure out how to optimize for that space. Cool. Yes, so this was all implemented in Theano currently. TensorFlow, the research on the DCGAN started before TensorFlow was released. As a lab currently, we actually use basically every framework internally. Still have probably the majority of our stuff in Theano, and at some point we'll probably be migrating to the likes of TensorFlow. Yeah. All right, thanks.